Pond snails typically live in freshwater and can survive both in the water and out of it, but require water to survive. The Physidae family is very common in the Americas and other temperate locations. In this case, the pond snails were stored in a milk carton with native pond water and plants. Pond snails prefer not to be in open areas and rely on shelter of plants such as these leaves and moss to feel safe. Pond snails mostly eat algae, diatoms, and detritus, including dead leaves. They are a very adaptable family and reproduce extremely rapidly and can tolerate pollution of their water source. Pond snails are not particularly large, typically only a few centimeters in height and millimeters in width. They are distinctive because of their sinistral snail shell, otherwise known as a left-handed tern, and are generally a translucent brown-yellow color. Snail shells are crucial for the survival of any snail. Pond snails have shells made of mostly crystallized calcium carbonate with small amounts of protein. Their shells prevent damage to the radula, which is basically the snail's mouth, and the foot, which contains the glands used to secrete the snail mucus we are concerned with. Here is snail A moving around the glass slide. At the end of the slide, I placed some pond water to give the snail some motivation to hopefully move across the slide. I let the snail crawl around a bit before I started recording so it could acclimate to its surroundings. As you can see, the snail is going all over the slide and he eventually makes it to the pond water. I also sped this up by a factor of 5,000 so we didn't have to watch him move across the slide for 6 minutes and 44 seconds. Here is snail B moving around his slide. He doesn't seem to want to move toward the pond water very much, but you can see him moving around and exploring the slide. I sped this up by a factor of 3,000 because this was also pretty long. Here is the fluorescent staining of snail A tracks at 10 times magnification. I used a lectin called concanavalin A, which preferentially binds mannose, and washed it 3 times with water and then with 70% ethanol to precipitate the protein. As you can see, there are several deposits where the con A bound to the snail track. The stars denote deposits that I felt were significant based on my observations on other parts of the slide. And here is snail B at 10 times magnification. There are heavier deposits of mannose, but snail B also moved around less than snail A and tended to stay in the middle of the slide. Again, the stars denote significant deposits of mannose. I stressed the snail out by placing him on the slide and then poking him 3 times in the back, which resembles predatory behavior. This is the same snail from the previous snail A video, and you can see the marked difference in his behavior between the two. He is doing everything he can to get off that slide. I followed the same protocol for snail B, and he is so stressed out that he's not moving. In real life, he probably would have been eaten by now. I tried to move him, but to no avail. The same staining procedure was followed as the previous fluorescent slides. You can see that snail A did in fact produce a froth track that kind of looks like sea waves with mannose throughout. It was interesting to notice that there was bound mannose in both the froth and heavier deposits, which I was not expecting. Both are denoted with stars. Snail B's inability to move meant that I could only stay in one part of the slide. You can see that there are only thick deposits of mannose.